Okay, hi. My name's Abe Stanway. I'm a data engineer at Etsy.
My name's Cowie. I'm a senior ops engineer at Etsy, and what we want to talk to you about today is bringing the noise, which is how we're making sense in a hailstorm of metrics.
Before we get started, we realized 90 minutes is kind of a long time, so we're just going to break down the agenda of the talk. So we're going to spend the first 10 minutes talking about motivations that led us to build this thing that we're going to show for you today, and the kind of background work that has already been done and its shortcomings. And then we're going to dive right into a deep dive into the architecture and algorithms behind both Skyline and Oculus, which compose our Kale monitoring stack. And then if you're still awake, we're going to show you a cool demo, which hopefully you will be awed by, unless it fails miserably. Either way, it'll be a good time, so you should stick around. And then we will open up the floor for questions. So let's get into it.
Yeah, so this is just to sort of frame the background of where we're coming from, what our business actually does, and what our motivations were in trying to solve the problems we're talking to you about today. So we're Etsy. We're the world's leading marketplace for handmade and vintage goods. And just to give you a couple of stats, we have about 1.5 billion page views, 117 million US dollars goods sold, and 950,000 users. And this was in December 2012. So we're a decent sized site. We're not Google, but we're not tiny either. So we have a decent amount of traffic, and we have some interesting problems that we hope we can share some insights on.
We practice a thing called continuous deployment, and we can define that. So to deploy code is pretty straightforward. It's to add new features onto your site while it's being heavily trafficked and hopefully not taking it down. And since we are so heavily trafficked and we are making money at all times of the day, every second, we want to add new features, but without stopping this flow of revenue.
Yeah, so we have around 250 committers. Some of them are engineers, some of them aren't. But our one golden rule is that everyone deploys code. In fact, on day one, first day at Etsy, you'll deploy the site. You'll put in your picture on the About page, but you'll deploy live code.
And we make it really, really, really easy to do that. All you have to do is push to master, push the big green button, and then that will do a bunch of crazy things behind the scene, but it will result in your feature being shown live to the world to see. And with this process, we get around 30 plus deploys a day. Keep in mind, that's not 30 commits a day. In each deploy, there's about 8 commits involved. So there's a lot of people doing this at all times of the day. And you're probably thinking, like 30 deploys a day, is this like a safe thing to do? It sounds like 30 times that you're messing with things, that things can go terribly, terribly wrong.
Yeah, so we like to think we've made the process as safe as we can, but stuff still goes wrong. But instead of fearing human error, what we try and do is optimize for quick recovery by anticipating problems and dealing with them quickly, instead of fearing human error, as I said.
And so to that effect, we really try to have a complete coverage of exactly what's going on in our entire network stack so that we can detect when things are wrong quickly and then be able to recover from them. And so to that end, we have a whole slew of monitoring tools that we've implemented.
Yeah, so some of these tools you recognize, some are not homemade, some are homemade. On the not homemade side, we have Ganglion Graphite for collecting all of our graphs. We have Nagios for generating alerts. And then on the homemade side, we have StatsD, which Theo mentioned before. It was open sourced a couple of years ago. It basically lets you makes it easy to collect metrics from throughout your applications and so on. We have SuperGrep, which is our real-time error logging system. And then we also have Skyline and Oculus, which is what we're going to be talking to you about today.
Mm-hmm. So the kind of first line of defense that we have for things that can go wrong, that need to be monitored, is with SuperGrep. And this is a really, really simple real-time error logging tool. And the way it works is it's a simple node daemon that is tailing log files. And literally all it's doing is it's going tail f access.log pipe grep -v things that we already know are going on, error. Okay, so what you end up with is all the errors that you don't already plan for will show up on SuperGrep, and they will stream by. And since we're always being trafficked, if there's something wrong, you're going to get a lot of errors in SuperGrep. And so in Etsy parlance, you say, is SuperGrep blowing up, or is it angry? Because you see a sea of red here. And that's one way to know that things are really messing up.
So this works to a point. This is good for capturing errors that capturing things that break that throw errors. They put something in PHP error log, they put things in the Apache error log. The thing is, not everything that breaks throws an error out of the box, and even if it's not broken, it's just kind of doing something interesting. It might not tell you that out of the box, so how do we actually capture that information?
So to deal with this, well, not we, but Etsy wrote a tool called StatsD, which probably a lot of you are familiar with. And it's really, really simple. If you want to measure something that is not necessarily a hard and fast error, you can very easily by sticking in the StatsD call anywhere you want. And so we make it really, really easy for engineers to do this. And then when they do, you get an entire metric time series, magically appears in Graphite, and then you can analyze it, you can put it in a dashboard, and you can do whatever you want with it. And that is enabled because we have a philosophy at Etsy of if it moves, graph it, right? Anything that moves, you want to graph. And so we want to make it really, really easy for people to do this. Because if there's friction around graphing things, no one's going to do it.
Yeah, and if it isn't moving, you probably want to have a graph for it anyway, because just because it's not moving now doesn't mean it might not move in the future. So assuming we're now capturing our metrics, how do we actually make sense of those? So the kind of industry standard at the moment is dashboards. Etsy have an open source dashboards framework, a bunch of other people do as well. They're very much the kind of de facto way of collecting together your metrics into one place. The thing with dashboards is dashboards are essentially a manually curated collection. They're things you know are relevant or you know are important, and you want to put them in a position of prominence. So that's a good starting point. Dashboards help you kind of get a good hand on the things you know are your most important or your most relevant metrics.
But the problem is when you have a philosophy of graphing everything, and when you make it really, really easy for people to do this, you end up with an avalanche of metrics, right? You end up with so many metrics that you can't possibly keep track of. And at Etsy, we have 250,000 of these. And at that scale, the dashboard paradigm kind of just completely falls apart, right? You can't make dashboards of 250,000 metrics. If you tried to, you would be in trouble because you'd have 250,000 dashboards. And we've got 250 committers with 250,000, so that's a dashboard to engineer ratio of 1 to 1,000. So that's not really going to work, right? And if you wanted coverage in that kind of way, you'd have to have all your engineers doing nothing but looking at 1,000 graphs all day long for bad things that can happen.
Yeah, so that brings us on to the question of if we have a graph and it's not on a dashboard, so no one's looking at it, and that graph spikes, does it really spike? Is there any point in us even having that graph? So how do we then capture this information in a meaningful way that makes sure people can actually do things with it? And the sort of standard out-of-the-box approach to doing this is Nagios. Nagios makes it very, very easy to alert on Graphite stuff. You can alert on metrics across the board. But again, when you're dealing with a high metric volume, this kind of breaks down. As Theo mentioned in the last talk, if you have an alert that doesn't have a meaningful remediation item, and it isn't actually a meaningful alert with a meaningful threshold, it's kind of a pointless alert. You're going to ignore it, and you're going to end up silencing it because it keeps waking you up. So when you're dealing with 250,000 metrics, you're in a position where you can't possibly have meaningful alerts for all of them. So again, the Nagios model kind of breaks down a little bit here.
In addition, there could be relationships in between your hundreds of thousands of graphs that you don't actually know about, because you would notice them if like something bad happens, if a server goes down or something. You see a lot of graphs that kind of spike or go down at the same time, and you can see that from a distance by looking at the dashboards. But if these dashboards aren't there, or if you're not looking at them, you're going to miss those intricate kind of relationships. So our problem has been boiled down to a two-sided problem. And that is the problem of unknown anomalies and unknown correlations. And to fix this, we made Kale. So Kale is the name of our monitoring stack. And it's composed of two parts. It's composed of both Skyline and Oculus. So Skyline solves the anomaly detection part, and Oculus will solve the metrics correlation part. And so now we're going to do a deep dive on both of those.
So the first question we were asking ourselves that we were trying to solve is how do you analyze a time series for anomalies in real time? Just one time series for the moment. Luckily, this is quite easy to do. The vast majority of our metrics live in Graphite. Graphite has an API, exposes your metric data as JSON. It's very, very easy to get out. You can make an HTTP request to Graphite. You can get your JSON data out. It gives you all the raw values. You can run your algorithm of choice over that data, and it will give you can get a true or false value for whether that data is anomalous.
But when you have 250,000 of these things, that's not really going to work, right? You can't be sitting there making 250,000 HTTP requests to Graphite every second to try to get that data. It lives on Whisper files on disk, and disks cannot support that kind of throughput. So we needed a solution, and that's where Skyline came from. So that's what we did. So to reiterate, Skyline is a real-time anomaly detection system.
But for those of you who are maybe thinking real time, hang on a second. It's kind of important for us to frame what exactly we mean by real time. We're not talking a financial trading system that's dealing in sort of nanosecond timescales here. So what we're defining real time here is kind of real time.
Yeah. So so our stats D, the resolution that we collect stats D on, is 10 seconds. So every 10 seconds we flush to graphite, and so you're not going to get a stats D resolution of more than 10 seconds. You can set it for more, but we don't do that. And with ganglia, we also use ganglia. We use a 1-minute resolution for a lot of our metrics. We do use a 10-second resolution for some ganglia metrics, but a lot of them are 1 minute as well. So in the very best case scenario, you're going to get 10 seconds to a minute, assuming that you are able to process them all instantly. But we don't. It takes about 90 seconds to actually then take the data, process it, analyze it for anomalies, and then surface it through the web app.
Yeah, so what we were going for is, in this context, real time is faster than you would have discovered it if you were looking at the graph at the time.
Cool.
So when we were looking at how to solve this problem, it became apparent that we were going to need some kind of memory. We were going to need to store this data in memory. If you're storing it on spinning rust, or even if you're storing it on SSDs, it's going to add a lot of latency when you're trying to get that amount of data that quickly. So it became apparent we were going to have to store this data in memory, and the solution we ended up picking for this was Redis.
And so the question becomes, how do you get a 250,000 time series into Redis on time? And of course, you're going to need some kind of stream of data coming through. And so we were looking around for this stream that may or may not have existed. And we actually found that we did have one, because we use graphite. All our metrics come to graphite. And so let's examine exactly how that goes down. There's a cool graphite daemon called the carbon relay agent. And the way that works is it's meant to be the actual listener on your graphite, and then you send your stats calls or whatever you're doing to the relay agent. And then the relay will relay both locally to the actual graphite that you're going to query on, and then it'll relay it to another graphite for redundancy. So this is great for when your first graphite goes down and you want to still have your metrics because you still need them even if your graphite's down, and you'll have a redundant graphite server listening. And the way it does this is it sends pickles to the backup graphite. And so, okay, well, here's a stream right here. We can actually take advantage of this, and we can configure Carbon Relay to stream not only to the backup graphite, but to Skyline. And so what we've got is a situation where the metrics are coming in, and it's streaming to both the backup and to Skyline. And the original graphite Carbon Relay has no idea that there isn't a graphite listening on the other end. And Carbon Relay is very good at relaying, because that's what it was designed to do. And so it can handle relaying to two different listeners at once.
Yeah, so a lot of our data is stored in graphite, but we also use other metric systems as well, Ganglia being the next biggest on the scale. Now, we use version 1 of the Ganglia web interface, which doesn't support all the nice CSV and JSON export. So we were faced with, how do we get this data out of Ganglia in some kind of in a short enough time scale that we can actually do interesting stuff with it. Now, a useful feature we discovered was Graphite out of the box will happily read RRD files, which is Ganglia's native storage format. So what we're actually doing is we're dropping Graphite on top of our RRD files, which gives us JSON representation of all of our Ganglia RRDs very, very easily. What we then have is we have a simple import script, which is basically running on a continuous loop, and it just grabs the latest minute or whatever interval of change data points, and it then squirts them into another listener running on the Skyline side of things, which just takes a UDP packet that's formatted metric name, timestamp, value, very similar to the statsd format. And then this also gives us the flexibility when we want to add in more of our metric systems, because we're still working on, for example, Cacti and Fitbee. When it comes to do that, we already have a listener set up that we can just squirt data points into as fast as we can get them from our metric system.
And keep in mind that you don't actually need to have Ganglia or Graphite installed. We have listeners that you can just ping metrics over UDP or TCP to the Skyline listener, and it'll happily receive them. And so, okay, so we have our stream of metrics, and we need to figure out what to do with it. We need to figure out a way to store time series. And we've already gone over that we're going to do it in Redis somehow. And we have to keep a couple things in mind when we do this. We want to minimize both I/O, and we want to minimize memory. And so on the I/O side of things, you have to keep in mind that you're going to be writing metrics lots of times per second, and you're also going to be reading them on the analyzer end, because you're going to be taking them out and analyzing them. So Redis has to be able, so you have to like really watch your load on Redis, or else you're not going to be able to withdraw them on time, or you're not going to be able to add them on time. And so Redis has a lot of cool data structures that you might think are intuitive to use for time series. Like you can use lists or sets to do this stuff. But those have, they're expensive. Lists are expensive to withdraw from Redis, unlike regular strings, which are, you can withdraw and set in constant time. And there's also a great feature that Redis has called the append feature, where you can append onto a key in atomically, and do it in constant time. And so all our keys are, the names are the metric names, and the values are the actual time series. And so we're sitting here appending to those strings the data points as they come in. And this way we can easily withdraw the strings as well, because it's very easy to get strings in Redis.
So now we've actually figured out how to get the data into Redis. What format do we store it in? We need to be able to do things with this data. Now this is usually where the name JSON would start marching with ill-deserved confidence towards this presentation. Because JSON is very easy to use. It's machine readable. To some extent, it's human readable. So if we, for example, we're looking at statsd.numstats, the number of statistics statsd is looking at the moment, we have a timestamp value pair in Redis. If we want to append to that, we simply stick another one on the end. It's a very simple format. Every time we stick another one on the end, we just add a new metric to the bottom. But there's a weakness here. What we discovered was that using JSON, although convenient, incurred a massive performance penalty. In fact, we discovered that over half of the CPU time that we were spending on this analysis process was spent decoding JSON.
Yeah, and that's a pretty silly problem to have, right? Because you should not be using valuable CPU resources, which should be reserved for the actual algorithms that we run on the data. It shouldn't be spent decoding the data so we can actually run the algorithms in the first place. And we can briefly go into why that is. So here's a perfectly valid JSON string. And if we break it apart, we realize that the only things that we care about in the string, there's only 2 tokens in there out of 5 of actual data that we need. And the rest is brackets and commas, which are used to kind of demarcate the data structures. And the CPU uses these to, as it's decoding the string, to know, like, okay, this is an array now because I found it into the bracket, and I'm going to decompose it this way. The problem is, in JSON, there's no metadata. So there's no way to tell the CPU to optimize for, to read X number of bytes on the string. It has to read every single one looking for brackets or commas or quotations or anything else. And so this is really expensive because you're doing a full string scan, and that's no good.
So this is the solution we came up with, MessagePack. But this slide actually quite accurately conveys the feeling we had when we figured out that MessagePack existed. MessagePack is a binary-based serialization protocol, and I'm just going to go into a little bit of detail on what it actually looks like. So this is an example of MessagePack. The key thing here is the first byte of that section is the array size. So all of a sudden, we now have this metadata that lets it only go X number of bytes into the string to get the array we care about. So we now have things we care about and one extra 16 or 32-bit big endian integer that tells us how big our array is. When we want to append to that, we just stick another MessagePack string on the end of it. It's also got the array size that's about to follow. So it avoids this problem of having to do a full string search on 1,000 value long time series just to be able to actually parse it into some kind of usable data format. And what we ended up discovering was once we switched over to using MessagePack, we ended up cutting in half the amount of CPU time that we were using during this analysis process.
Yeah, so we really highly recommend MessagePack for just about any place you would normally use JSON, unless you're talking to a browser.
Just out of interest, MessagePack was originally designed for RPC stuff, for inter-process communication, but it actually turns out to be really awesome for this kind of use case as well.
Okay, yeah. So you know that we're appending the data, but if you were to do this forever, you would eventually run out of memory because you're only appending to time series. They're getting longer and longer and longer, and that's not really going to work because eventually you will run out of memory. So we needed to find a way to kind of chop off old data points. And so we've got a Roomba process that goes through, withdraws each time series, and chops off the old data points older than a certain duration, which is configurable. And so in this way, each time series, you keep a rolling duration of each time series in your data, and that's what you actually analyze. And this is okay, like for reuse a day, this is okay. You lose historical data, but when you're doing operational monitoring, data that's really, really old kind of gets less and less useful because that's not what's normally happening. It's harder, like you capture long-term trends, which you don't necessarily need to detect anomalies in the short term. So we found that a day is sufficient for our needs. Your needs may be different.
And actually, another interesting thing that came out of taking this approach of having this Roomba that gives us this rolling interval of data was when it came to actually doing the search stuff for Oculus, which we're going to talk about later. We discovered that because the algorithms we're using are quite expensive, searching over 24 hours of data is unnecessarily time-consuming, and it's not actually that useful for what you're looking at the moment. So this approach enabled us to capture a 1-hour snapshot of the data as well, with relatively little performance penalty compared to having to have an entirely separate copy somewhere else.
And so now you're saying Roomba.py? This is Python? Why'd you do that? Yeah, we wrote it in Python. We chose Python because it has really awesome statistics libraries. And although its concurrency model is terrible, we had more faith in our skills as engineers than we did in our skills as statisticians. So we opted for the slog in the parallelism side of things in favor of an easier time implementing algorithms. And so we take advantage of libraries like Pandas, stats models, SciPy, and NumPy. These are pretty robust tools that have really helped. Yeah.
So yeah, the analyzer process is multi-process model. It's fairly straightforward. It takes all of the Redis keys, it assigns a bunch to each process, and then each process will decode the metric. It will analyze it using whatever algorithms, and then once it's finished that, it will write them out as JSON. We just basically dump all of the metrics we think are anomalous out to a JSON file, and then the front end runs every 30 seconds using set interval. It reads in that JSON file, and it displays it for you in the UI.
Okay. So for a quick taste of what this UI is, we're going to do a full demo later, but this is what it actually looks like. You can see, you got the short hour view on top and the 24-hour view on the bottom. The red line is the actual data point that triggered detection that you can see relative to the other data points. And you can see at the bottom the list of anomalous metrics. And that's actually what gets written out as JSON to disk, right? In addition to the actual data point that triggered detection. And so that JSON file is just read by the front end and written to by the back end. Okay, so but we've talked about anomalies a lot without actually defining how we detect them. And so this is how we actually go about doing that.
Yeah, so the way Skyline works is it uses a consensus model. The thing with anomaly detection is all time series are different. Everyone's data is different. Everyone's use cases for this are different. So it would be incredibly arrogant of us to pick one algorithm and tell you all that this is the definitive way to detect anomalies. It's awesome and it will work perfectly for you, because chances are it probably won't. So what we actually do with Skyline is we have a consensus model. So we implement out of the box. We have 7 algorithms that we've implemented, and the way this works is they all vote on whether they think a time series is anomalous. If 5 out of the 7 agree that it is anomalous, then that's flagged as an anomaly.
Yeah, and so with this strategy, you can basically just implement everything you can get your hands on. Read any kind of paper that you think might help, implement the algorithm, return a Boolean after running that on the time series, and see if it works. And the cool thing about this is that some algorithms work well for some time series and others don't work well for others. And so when you use a majority kind of votes model, chances are that the rogue algorithms that return positive will kind of get balanced out by the rest of them. At least you would hope. And so the basic algorithm that we use is derived from standard process control, which was pioneered by Walter Shewhart in the 1920s. And it reads, a metric is anomalous if its latest data point is over 3 standard deviations above its moving average. So one more time. Each time series has moving averages, right? And there are standard deviations above and below that. And there's 1 standard deviation, 2 standard deviations, and 3 standard deviations, right? Or otherwise known as 3 sigma. And if your data point is outside the 3rd standard deviation, then chances are you've got an anomaly, because that's something that hasn't really been seen a lot. And there's a couple algorithms that we use that kind of riff on this theme. We're going to go into a couple of them. One of them is the Grubbs test. So the way the Grubbs test works, it's a standard model for outlier detection. And you pass in your data point that you want, subtract the mean from that, take the absolute value of that, and divide it by the standard deviation. And that's what's called a z-score. And if that z-score is greater than what's called the critical value of the t-distribution, which is just a fancy way of saying, you got your distribution and you have the 5% at either end. The stuff in there is part of your t-distribution. If it's greater than that, then you've got an anomaly. And we also use an ordinary least squares model, which is a type of linear regression, where we make a best fit line to the data and make predictions off it. And if the latest data point is outside of 3 sigma of the predicted data point, then we've got an anomaly. So those are just 2 different variations on that basic algorithm.
Yeah, and another approach we take is histogram binning, where you can essentially generate a histogram of your time series, and if you have the particular value you're looking at, if the bucket that ends up in is very, very small, then chances are that might actually represent an anomaly because everything else is in a bucket of a different size. So that gives us a bunch of algorithms to deal with, but this is not a perfect solution. There are some caveats to this approach.
4 of them, to be precise. So we're going to kind of lay it all on the table for you, and hopefully you can come help us think through it afterwards. So in order, they are seasonality, spike influence, normality, and parameters.
So let's look at seasonality first. This time series represents a 24-hour period of data, and it has a clear anomaly in it. There's a massive spike in the middle of the graph. Any rational anomaly detection system will tell you, hey, this is unusual. But if we expand the time series, we actually see that this same feature reoccurs every single day. This may be, for example, a nightly backup, or something like that. It's perfectly normal, it recurs, it's a frequent event. I mean, it might still be an anomaly, but there's also a chance it might not be. And at the moment, the approach we're taking does not account for this seasonality of events. And spike influence as well. What you can see here, if you look about a third of the way in, we've detected an anomaly. This is fantastic, the system works, let's all go home. The problem is, now we've detected this spike, we've also shifted the moving average of the graph. As we mentioned, for example, the basic algorithm we're using is 3 standard deviations above or below the moving average. But this spike's now bumped up the moving average. So as you can see under the red line, there's another anomaly which we're actually missing because it doesn't get caught by this approach. There are ways around this. For example, once you've detected a spike, you can effectively smooth it out of the graph so that you're not influencing your moving average. But this, of course, means you're deleting data. Effectively, you're deleting past data that you might need for other algorithms. So this is something else that our current approach doesn't solve, and that we want to focus on doing a better job of counting for in the future. There's a question there. Say again, sorry? Sure, yeah, we could take the moving average just after that point. But it's one of those things where we didn't feel comfortable with one solution that we could absolutely guarantee would work for everything. So we're kind of presenting this out there as a known limitation of the system so that, if we push out a fix, everyone can look at it and say, well, actually, that's a bit of a silly idea. I have a better one, and then give us a pull request. I
mean, also another problem with using an exponentially weighted moving average is that, a day is long enough to kind of get a full view of what is normal. And so if you only weight the things that have recently occurred, that doesn't necessarily mean it's normal at that point. So you kind of lose the advantage of having a larger sample size when you do that. And speaking of sample sizes, the third horseman of the model apocalypse is normality. And so the standard deviation algorithm assumes that your data follows a normal distribution, right? And so that way you can look at 3 sigma from the normal distribution, look at the tails of that, and calculate the anomalies from there. But real-world data doesn't necessarily follow a normal distribution. And so these algorithms kind of fall apart when that's not true. Or you can have uniform distributions where you just emit the same value at the same time, or degenerate distributions, right? So there are lots of distributions that actual data take. And we have a question.
Yeah, have you thought of the fact that Skyline is almost analogous to an electronic trading system that's used by stock traders or currency traders? And a lot of their algorithms are open and available. If you incorporate some of that into this, you won't have to reinvent or have to re-look into these graphs. If you just decide the data that it's actually doing, all it is data with spikes and stuff. And you can have it trigger events based on what you see. That's what an electronic trading system.
So that question was, have we considered looking at the kind of algorithms that stock trading uses for events as well?
Yeah.
Good idea.
Well, I mean, yeah, so it is, but it also, like a lot of those, they tend towards forecasting algorithms. Which kind of imposes an opinion on the kind of models that you can take of your data, right? And there's also like meteorology, like they do ensembles all the time where they have different types of linear regression, and they all make a forecast based on different models, and then you kind of average out the predictions together and get your model that way.
Isn't that what you want to eventually do?
We do, but we don't necessarily want to impose an opinion on how it should be done, right? Because then you're excluded from doing things like histogram binning or from other kind of spunky algorithms that may actually be very effective. So That's why we chose not to do that. And then the last portion of the model apocalypse was parameters, right? So there are very effective ways to fit models to data, right? If you tweak parameters for them, right? You can use your whole winners, you can use your Box-Jenkins, and you can use your ARIMA models to do this. But for them to be actually effective, you have to manually go through and tweak the parameters to actually fit the model to the data. And with 250,000 metrics, this is infeasible, right? You're back at the same problem of having too many Nagios alerts. Because at that point, you might as well just make a proper Nagios threshold for that. So that's a problem. And so as from going forward, like this is open sourced, but kind of filling out these problems with the algorithms is the current focus of this project moving forward.
Did you look at Bayesian, any Bayesian models to
Right.
front or in line with this stuff?
So the question was, have we looked at Bayesian models, which are non-parametric models, and those are that's what machine learning is all about. We haven't done that yet, but it's certainly an option.
So we've detected our anomalies. The next question is, we have our anomalies, or in some cases we have a time series that possibly wasn't picked up as an anomaly. How do we find all the other metrics that are doing the same thing? How do we correlate across all of this 250,000 time series worth of data to identify metrics that are exhibiting the same behavior, whether anomalous or not? So this was where the idea behind Oculus came from.
So Oculus, it's a way to correlate lots of metrics together. And when you talk about correlation, you could start thinking in terms of graphs, like actual images that look the same. Because that's what we do when we correlate with our own eyes. We look at the graphs. And so when we were first casting about a solution to solve this, we thought we might compare the images using some kind of spectral analysis or some kind of image comparison technique. But that turned out to be really, really super expensive and slow.
It's really hard to do as well.
Yeah. And so we opted to just use the raw time series that we already, in fact, had, because it's already in Redis from Skyline.
Yeah, so as we all know, there are hard problems in computing. Naming things, cache invalidation, numerical comparison, not one of them. Numerical comparison it's relatively cheap to do. There are amazing amounts of algorithms out there, and it's it's a nice way of approaching the problem.
So one of the algorithms that we first came upon for comparing two time series, it's stupidly simple. It's called Euclidean distance. And all you're doing is you're taking two time series, superimposing them on each other so that they share an x-axis. And then for each x value, you're diffing basically the y values. Okay? So for each x value, you get the difference between them. And then you sum them all, do a little bit more math. It's not really in the scope of right now. But then you end up with a difference between them in terms of just raw length. And so you can imagine if you have two time series that are coincident, right? So they're exactly the same time series. The difference between each y1 and y2 is going to be 0. So there's going to be a distance between them of 0. And so that's how you know those are exactly correlated. And the greater that distance is, the less correlated the two time series are.
So the thing with Euclidean distance is it's both easy to code and it's very, very cheap to calculate, but it does have a significant weakness. And that largely comes down to the fact we're dealing with real-world data. To look at ganglia, for example, a lot of our ganglia metrics are generated on a 1-minute cron. And there's no guarantee those crons are all going to fire at exactly the same second, which means when we get our metrics into Redis, they're not necessarily going to have exactly the same timestamp, even though visually the metrics the time series look identical. The problem with Euclidean distance is because it's only doing literally linear distance. If you have your second time series shifted by one data point to the left on the x-axis, your Euclidean distance is going to be possibly extremely large, even though to the naked eye, the time series look very, very similar. So how do we counter this problem? There's another algorithm out there called dynamic time warping, which is a lot more computationally expensive and there's a lot more to it, but it's essentially designed to solve this problem to some extent. Dynamic time warping helps with what we call phase-shifted data, which is data that's identical, but it's shifted or stretched on the x-axis. So if you imagine you have the scenario I mentioned before, where you have virtually identical data, but it has a slight shift or stretching in the x-axis because one cron fired a couple of seconds later, what dynamic time warping will do is it will pick up that correlation. Now, the way dynamic time warping works is a little bit more complicated. I'm not going to go into too much of the maths, but what it essentially does, if you imagine you have a grid and it lines up your two time series on each side of the grid, on the one on the y-axis, one on the x-axis. What it essentially does is it tries to figure out the shortest path through the grid. And if you imagine you have some stretching on the x-axis, you might have it's going up at a 45-degree angle, and then there's some stretching, so it'll move across 3 points, because this one data point correlates with 3 on the other axis. So that would be an example of the x-axis being stretched. For example, a line that goes up across for a few data points and then back down again. So this is good. This is a great algorithm. As I mentioned, it's kind of expensive, but essentially this means, again, we've solved the problem. Yay, we can all go home. Except.
So we did it, right?
Yeah.
No, we didn't do it. That's because dynamic time warping is really expensive. It runs in exponential time, which could possibly be okay, except when you account for the fact that our time series are hundreds to thousands of metrics long. And not only that, but we have 250,000 of them. So it was pretty slow. We saw it taking about 20 minutes to half an hour to do a full run of everything. And this could be okay in some situations. If you're in academia and you have a large data set that you want to correlate, you can just turn your server on, let it cook, go out to lunch, and then come back and get your results. But when your site's down, you don't want to do that. You want the data right now. You want to know exactly what's correlated with everything else, so you can diagnose the problem and fix it before you stop losing more money. And so we needed a faster solution.
Yeah. So how do we solve this problem? We have a really, really good algorithm, but it's incredibly expensive to use on the amount of data we're looking at. Now, what we realized was there was actually no need to run dynamic time warping on all 250,000 metrics. What we're typically dealing with when we're looking for correlations is the ones that are most interesting to us are maybe the top 10 or 20% of the metrics, say the top 10 or 20,000 in this case. Wouldn't it be great if there was some way that we could discard obviously dissimilar metrics before we've done this expensive algorithm? If we could somehow, so for example, to use the analogy of the human eye, if you scan down a list of graphs, you can tell at a glance that some graphs are totally unrelated. One has a big spike in the middle, the other's totally flat. How do we get the computer to do this for us without crunching all of this numerical data?
So to do this, we use a technique called the shape description alphabet. And what it's really doing is reducing the resolution on your time series to its core features. And it's pretty simple. All you do is you take the difference of 2 adjacent data points, and you assign it a token in your shape description alphabet. And we have 5 letters in this alphabet, and that is sharp decrement, decrement, flat, increment, and sharp increment. So depending on the magnitude of the difference between the 2 data points, they get one of these letters, and you can make a representation of your entire time series this way that has less detail, but that retains the significant features of the time series.
Now, as some of you may have spotted, there's a problem with this in that this approach assumes that all of our time series are equal in magnitude, which of course this is the real world. That doesn't happen. Some of our time series go from 0 to 100, some go from 1,000 to 1,000,000. If we have this static alphabet where we're fitting everything into boxes, so how do we manage to make that work for all of our time series? The answer is we normalize the data. What we actually do is we take our original series of values and we scale that down to between 0 and 25. So we take the lowest value in the time series, make that 0, the highest value, make that 25, and we assign every other number a position in between. Now this obviously loses a lot of detail in your time series, but that's okay here because this is a rough pass. We don't care about getting really, really detailed fine-grained results. What we're trying to do is do a very rough pass, as rough and as cheaply as possible, to get rid of as many metrics as possible that we can easily tell are very obviously not correlated. And just as an aside, what we actually do with the fingerprint as well is we discard the points that show up as flat. Because something we discovered was that if you have a data point time series, which is, for example, predominantly flat, and then you have one spike at the end, because of the approach we're taking, which we'll come on to shortly, you can end up basically having false correlations because time series have so much flat data that's outweighing all of the other stuff. And the things that are typically most interesting to us are increments and decrements and that sort of features. There are cases where you might want a graph, if a graph goes flat, it's literally like a heart monitor stopping. That's actually quite interesting to find out when that happens. But for the moment, we're assuming that flatness isn't interesting.
And so what we've got here is a string that's just a text string with tokens in it, and we want to compare those with each other. And this is a basic search problem. This is kind of a solved problem. There are tools to help us do this. So we chose Elasticsearch to literally just search through our shape description alphabet fingerprints. And all we're doing is we're taking the time series that we want to search for to find ones that are roughly related and searching for them in Elasticsearch, right? Because that will return strings that kind of look the same as the original string that you searched for. And so in this way, that returns a set of results that is a lot less than the original 250,000. And then you can run your original dynamic time warping algorithm, the expensive one, on the smaller sample size of results because you have fewer of them. And you can afford to make that kind of expensive concession.
Great, so surely we've solved the problem now. Not quite. We're still dealing with an order n squared complex algorithm. It's on roughly 10,000 metrics now, but the important thing here isn't the number of metrics we have, it's how long they are. We're still dealing with metrics that are hundreds to thousands of data points long. The longer they get, the exponentially longer dynamic time warping will take to compute its warp path. And this is still too slow. We're talking about, just to give you an idea of where we're coming from, looking at the volume of metrics we're looking at, this will now, if we do this first pass approach and then do dynamic time warping, it'll maybe take 4 or 5 minutes to give us our result across the entire lot of all those comparisons. This is okay in some circumstances. It's not an appalling number. But what we're looking for here is to give you timely operational awareness. So if you're sitting at a web interface and you have to wait 5 minutes for it to tell you what correlated graphs you have, you may have already fixed the problem by then. That's not actually that useful. So how do we solve this problem? Well, luckily for us, there's an alternate implementation of dynamic time warping called fast dynamic time warping, which got a lot of the way towards solving this problem for us. Now, fast dynamic time warping is order n complex. That means as the time series grows longer, the amount of time taken to compute the warp path increases linearly, which is much more attractive to us. Now, the way dynamic time warping works fast dynamic time warping, does come at the expense of a little bit of accuracy, but that loss of accuracy is configurable, which is good for us. So the way this works is, first of all, it coarses your time series. And what that means is it takes your initial time series and it reduces it to the minimum number of data points that will accurately reflect the shape of your graph. What it then does is it does the same thing as regular dynamic time warping, and it computes the warp path to give you to account for stretching the x-axis and so on. So this gives us very, very broad brush similarity. And that's the projection stage, sorry. What it then does is it refines these warp paths. Now this is where we gain the performance benefit because this part is configurable. It takes its initial rough warp path and it then looks outside of that to a configurable radius to look for more accurate warp paths. Now the neat thing here is you can configure how wide this radius is. What that essentially means is if you say you have a default radius of 5, which is the one we use, if you're running a search that works well, that's all well and good. If you're running a search that happens to include a lot of really, really long time series, and this ends up being cripplingly slow and you end up timing out because we don't want to keep you waiting for 5 minutes, you can dial this radius down. You can say, okay, I will accept possibly instead of a radius of 5, a radius of 2. I acknowledge I'm losing a little bit of accuracy, but it's gaining me the ability to run this search in a timely fashion. So this was a good trade-off, particularly because it's controllable, and it's also controllable by the end user who can make those decisions on how much accuracy they're prepared to sacrifice in order to make it work quicker and quicker.
And so, so just to recap how we actually do this, we use the phrase search. We use what's called in Elasticsearch terms a phrase search, a phrase matching search, for the first pass scores across all the shape description fingerprints. And the way that works, in a normal Elasticsearch search, it uses TF-IDF, and it tokenizes the entire string. With a phrase search, it treats the entire search query as a phrase, and it uses what's called a slop to detect out-of-order terms in what it's searching for. So we use a slop of 20, which means that if it will tolerate a maximum of 20 out-of-order terms to the original string. And if there is less out-of-order terms, then that's a closer correlation with respect to the original string.
Yeah, so because we have this configurable slop, this also gives us the ability to control the size of the initial bucket. Now, again, like we were saying, we're coming from a place where we have 250,000 metrics, and we want to reduce that to maybe 10 or 20,000. A slop of 20 works great for that. If you possibly have you only have 5,000 time series that are 10 times as long as us, maybe you want to expand that slot to tolerate 100 out-of-order terms. That's configurable too, so it lets you configure, firstly, how much stuff gets through the initial funnel to the refinement algorithms, and then it also lets you control what kind of performance penalty you're willing to accept on the refinement stage. Now, the thing with Elasticsearch is some of you might be thinking is it's really good at text search, but how are we actually making it do basically numerical algorithms? Elasticsearch gives you the ability to define a custom scoring script. That's essentially saying, take the results of this query, which will return you a list of stuff scored. In the case of a phrase search, it will be scored by the number of out-of-order terms, and it lets you recalculate that score. So what we're doing here is we're using some custom Elasticsearch plugins, one for fast dynamic time warping, and we've also included Euclidean distance because, providing you understand its weakness, it can still be useful. And what we're doing is we're then taking the results that come from the initial phrase search query, and we're then running them through these custom scoring plugins to recalculate the scores on our top 10 or 20,000 metrics, which give us a much, much more accurate score of how closely correlated those metrics are. And what we're going to come on to now, just for those of you who are a little bit more interested in Elasticsearch, is a little bit more detail on how that's actually structured and how it all fits together.
Okay. So the items in the Elasticsearch index, they have 3 fields here. The first is the ID, which is the actual name of the metric. If you're familiar with Graphite, the way we do namespaces, we tokenize them with periods. And so we have statsd.numstats for an example there. And you've got your fingerprint, which is your shape description alphabet that you've already configured. And you have the values, which are the actual time series data themselves. And what we do is we store all this, both the time series and the description, the fingerprint, into an item in the Elasticsearch index. And that way, when we're using the phrase match search for the first pass, we can specify that we want to query the fingerprint. And then when we're using the fast dynamic time warping or Euclidean distance plugin for the second search, you can specify that you want to search the values. And you can do this all in the same index.
Yeah, so out of the box, Elasticsearch it's pretty smart actually. It does a really good job. When you index something, it will scan all your fields, it will figure out what type of data it thinks they are, and it will make some default assumptions. For example, if you index a string, it'll, out of the box, as far as I remember, it will treat it as if it's text. It will tokenize it by, for example, white space and common stop words. That doesn't always work that well for us, so we're actually using a couple of Elasticsearch mappings. Now, the simplistic overview of mappings in Elasticsearch is it's essentially something that lets us describe how we want certain items of data to be treated. And we're using this particularly in 2 ways. The first is to override this default tokenization behavior. As Abe mentioned earlier, Graphite namespaces don't have spaces in them, they don't have common English stop words. So it makes no sense to tokenize that name by white space. So for example, looking at the ID field, we tokenize that using periods, because that then lets us break down our namespace into individual components so we can filter them out later if we want to ignore certain metrics from certain fields. The other thing we can do is we can use what are called untouched fields in Elasticsearch. And these are fields which are not tokenized or analyzed at all. What Elasticsearch actually lets us do is effectively have 2 copies of a field, one of which is tokenized as normal, one of which isn't. And this is important for us because if you imagine you have a tokenized series of values, you've got each of your individual numbers as individual tokens. The way Elasticsearch works, when you pass this to your scoring script, it will pass through each one of those values individually. That's no good for us because we don't care about the individual value. We care about the totality of the time series. We want to take the entire list of values in one go, compare that to the entire list of values from every other metric. So that untouched fields is the way Elasticsearch lets us work with the tokenized data when we want to, but also get the untouched data so we can just shove it all into our scoring plugin in one lump. So we're going to go into a little bit more detail about what exact queries we're using to do this.
Yeah. So for those of you more familiar with Elasticsearch, this is an example of the first pass query. You can see that it says match at the top there, which is specifying that it's a phrase match search. And on the fingerprint field, we specify that our actual query is the shape description fingerprint that we actually want to query for, which is the time series that we're looking for correlations against. We specify the type is phrase, and you can see our slap there, which is configurable, is set to 20. Once again, that's the maximum number of out-of-order terms in the phrase that the query will tolerate. And then it will, from that, it will return a list of results in order of their score of how many out-of-order terms there are with respect to the original shape description fingerprint.
Yeah, so we then take this list of scores and we pass that on to a refinement query. Apologies, it's slightly squished at the top there. So this Elasticsearch lets you define a custom score query, as I said. It lets you take the results of one query and then alter those in some way. So what we're doing here is we're kind of shortening it slightly, but we're passing in the first pass query results. And then we're saying we want to run this Oculus DTW script. Now, the way this actually works behind the scenes is this is written as it's the DTW and Euclidean distance plugins are written in Java. They're compiled into a jar file. They're dropped into Elasticsearch's lib directory, and it just has those scripts sitting there for you to use. So we're saying, okay, we want you to use this script. This script takes a couple of parameters. We're passing it the query value. This is the value we're actually going to search for. So this is the raw values of the metric that we're trying to correlate. What we're then telling it is what field we want to compare that to on all of the other metrics, in this case values.untouched. Now, as I mentioned before, what the untouched field is the untokenized totality of the values that are stored in Elasticsearch. And what this will then do is it will take the initial scores, so that we effectively have our list of IDs that survived the first pass, this, in our case, roughly 20,000 metrics. It will then pass all of them to the Euclidean distance plugin as the original query as a string of values, and it will then get the corresponding field from all of the other metrics. We can then split that string up into an array list, and we can do our comparison, and then we return a score for each one, thereby refining the scores we have and producing hopefully a much more accurate list of how closely our metrics are correlated.
And so to kind of go over what we have so far, if we can. This is the Kale architecture from bird's eye view. You can see Skyline is on the left there, and it's fed by StatsD, which is fed into Graphite, which relays to Skyline. Ganglia also is relayed directly to Skyline, and then that's served by a Flask app that you can then query for your anomalies. And all that data flows right into a Redis instance, and we take advantage of the data in Redis to populate the Elasticsearch indexes. So we have a bunch of rescue workers that go through and populate that, and then it's served by a Sinatra front end. So we're going to talk a little bit about exactly how we populate this data. So like we said, the data is already in Redis. It's stored as message pack encoded strings. And we can use that instead of having another relay from Graphite to go to Elasticsearch. We can use that to populate your Elasticsearch indexes, which are the things that actually get queried when you want to make a query for correlations. And so we have a bunch of rescue workers whose job it is to go through to Redis, get all the keys in there, decode it from message pack, and stick it into the Elasticsearch index.
Yeah, so there was a trade-off here, though, which was that because with typical Elasticsearch workloads where you're maybe gradually trickling in new documents, what we're doing here is we're essentially, because we're repeatedly regenerating the index with the freshest data, rather than appending an Elasticsearch, what we're actually doing is we're cramming in the totality of the 1 hour's worth of data for all of our time series. Now the problem was, when that's running, this all works perfectly well, Elasticsearch supports it, but because of all the stuff it's doing under the hood, when you're running this update, it becomes very slow to run searches against Elasticsearch. And what this meant was it essentially reduced the frequency we could run imports, because otherwise you can't search for anything. And that's opposite to the way we wanted things to work. We want to keep the data as fresh as possible. You don't want to have to wait 20 minutes for your data to appear in Elasticsearch. So what we had to do was basically figure out a way to avoid this problem. And the way we did that was we have a rotating pool of Elasticsearch servers. So the way this works is you shovel your data into one index, and that index is then pointed to by the web application, which will then run searches against it. What we then do, the next time we want to run an import, we in this case use a pool of 2 servers. You can use as many as you want. It takes the second server, which is just sat there doing nothing. The web app isn't pointing at it. It brings that round. It purges the indexes, because another performance benefit we gained was when you're cramming that amount of data into Elasticsearch, it's much quicker to do it on a fresh index than having to overwrite all the data that's already there, because then Elasticsearch has to do a bunch of stuff about maintaining data consistency and making sure that you don't get partially imported data and all that kind of stuff. Much faster to just purge the indexes and cram it all in one go. But this is now safe to do. We can purge this index because nothing's looking at it at the moment. So we cram all the data in as quickly as possible, then we rotate it back to be the current live index so that the web app is looking at that one again, and the one that was live is just sat there waiting to be imported. Now, the way this works, somebody asked me this the other day, so I'll just go into a little bit more detail. This doesn't mean that you only have, for example, this is running on a 2-minute cron. This doesn't mean you only have 2 minutes of data in each of the indexes as they rotate. What you're essentially getting in one index is 1 hour's worth of data. When that rotates, the next one will have an hour's worth of data, but 2 minutes more recent. So essentially, the oldest index that we're using, in the case of using 2, will never be more than 2 minutes old. So what this essentially means is that your data in the search interface will jump up every 2 minutes. The reason for 2 minutes is because we actually got this running really, really quickly. After all these performance improvements, it actually only takes about 25 seconds to import all of the data from Redis into Elasticsearch. But what we discovered was, because we're using relatively complex search algorithms, what was happening was that we were rotating servers while queries were still running, because some of these queries can take 20 or 30 seconds to finish running. And that was kind of bad, because what that meant was somebody would be in the middle of waiting for search, and you'd suddenly get an error because the index just disappeared from under it. So the reason we picked 2 minutes is because that gives us reasonably fresh data, but it also it reduces the impact of this happening. You have a much better chance of getting all of your queries to finish before the data rotates again.
And so once that data is rotated, the Sinatra front end that we have set up, we'll query that specific index while the other one is still being repopulated. And that's what your users will use to query based on the most recent data. And then it will run the queries to Elasticsearch, run both of them, the initial phrase match rough pass and the fine-combed dynamic time warping, and render the results in order of their correlation, in order of what it thinks is the correlation. And you'll be able to see the actual graphs to judge for yourself if it's actually right, and if it constitutes a correlation that could be a related problem that you can then go diagnose.
Yeah, so when we actually render the results, just as an interesting aside, as some of you may recall, the data we're actually storing in Elasticsearch does not include any timestamps. We're only storing the raw data of the time series. When it comes to display them, we need to start caring about the timestamps again, because we have to display the graph on the interval it was originally written at. So what we do here, rather than keep an entirely redundant set of data we don't actually need in Elasticsearch, what we're actually doing is we're using the data we already have. So we take the list of results that come back from Elasticsearch, and we actually render the results from what's stored in Redis. Now, there is a slight risk here that the data in Redis might be a bit more recent than what's in Elasticsearch. But because we're running the imports and rotations so frequently, that's actually a relatively minimal impact. There's a small chance that you might end up seeing, there might be an anomaly at the very end of the graph, for example, that just popped into Redis that makes you think, well, actually, that's not really that correlated with the graph below it. But that was the trade-off we made to get this working this way.